Hello everyone. So in this video, we'll do a very quick summary of what we talked about in the last 3 videos. And essentially, we talked about 5, maybe 4.5 formulas. So we have permutation and combination. That's what we started off with. Permutation, you'll notice that all of those have order associated with it, and combinations have no order. So remember those 4 questions that we always ask. What is our n, what is our r, and then what is our order, whether there's order, and then whether there's repetition, right? So when there's order, we look at the r, or when we decide whether there's order, we look at the r. So within the boxes, so however many boxes we have, does it matter if I put an object here or here, right? So that determines order. If it does matter, then it's a permutation and it has order. And then we ask ourselves, is there repetition? So repetition, we look at the n. So of the n objects, if I use the object here, can I use the object here again, and so on? Right, so this is with repetition. So with the repetition, it's the formula is simply n to the r. With no repetition, the formula is n factorial over n minus r factorial. And remember, the denominator is where we cut off the order. With repeated objects, like for example, how many ways to rearrange the word banana, they're repeated objects. So again, we cut off the order. We divide off any order that repeats itself. Right, so this would be an example of, so the last two would be an example of order with no repetition, because we cannot reuse objects, and hence we have this factorial. When there's no order, that's a combination. So when it doesn't matter if I put the object here or here, then there's no order, it's a combination. And with no repetition, so I'm not allowed to reuse these objects, right? So I'm not allowed to pick an object twice. The formula, you'll notice, is very similar to permutation, except we have to divide off the order again. Right, so dividing off the order, meaning getting rid of the order, we said we have to take a look at the group size, how many ways to rearrange the group size, and that was r factorial. And then finally, no order with repetition, we have this formula, and this formula was very similar to the ones that we have here, where we thought of it as distributing r candies to n people. Right, so we'll do a few examples of this just to make sure that we understand the idea, but go back and take a look at those videos if this doesn't make sense so far. All right, so let's just do a couple of sample questions here. So question 1, the format of the telephone numbers in North America is specified by this numbering plan. So we have X, we have N, and we have Y. So we basically have something like this. Okay, so let's split each one of these apart, because we have basically the area code. So we'll call this the area code. We have the prefix, and then we have the postfix of the number. So for the area code, we said is NYX, right? So N, there are 8, right? There are 8 possibilities for N. For Y, there are 2 possibilities, and then for X, there are 10 possibilities. So for the area code, there are this many possibilities. All right, so the next is, we'll call this the prefix. The prefix is going to be NNX. So we have N, which is 8, times 8 times X, which is 10. That's the prefix. And then finally, we have the postfix, which is all X's. Now here, I guess we can use our formula. We have the same amount of objects. So our N here is associated with X. Our N is equal to 10. And then we have 4 boxes to put them in. So this is with repetition. Okay, so you can look at these 2 N's also as with repetition as well. Okay, so this is straight up just the product rule, because in order to create a telephone number, we have to have the area code and the prefix and the postfix. So we're going to multiply all of these things together. All right, so question 2. In a class of 30 students, there are 8 majoring in computer science, and 4 students are chosen at random to fill the positions of president, vice president, and secretary and treasurer. So we have president, we have vice president, we have secretary, and we have treasurer. Okay, so we can again look at this as 4 boxes, and these 4 boxes are different. So that kind of tells you what kind of problem we're dealing with. How many different ways are there to choose the student so that at least one of them is majoring in computer science? Okay, so I'm going to talk about 2 ways to solve this problem. One is the one that we talked about in the earlier videos, which is by cases. So by cases, we can solve the problem for 1 computer science student, or 2 computer science students, or 3 or 4 or 5. Or 3 or 4, no 5. Right? So we can have 1 CS student, 2 CS students, and so on. We could solve each one of these problems in turn. I don't think I will go for this way, although I would invite you to try it and see if you get a similar answer. From the 30 students, we know that if we are going to put them into these boxes, this would be a permutation. Why? Because if I get put as president, it's different than if I get put as secretary or treasurer. Okay, so this, we have n is equal to 30, and then we have r is equal to 4, and this is a permutation without repetition. Now, why is it without repetition? Because if I'm president, I cannot also be vice president, right? So these are different students being picked. So right away, we have this formula. Now, this formula is indicating if there's all of the possibilities to assign these students. Now, there are 8 computer science students, so you'll imagine that in this answer, some of them might be computer science students, but some of them might not be. Okay, so what we want to do is subtract off the instance where there are no computer science students. Okay, so 0 CS students. And what does that look like? Well, I can just take away those 8 students and I'll get 22 students and distribute them into these 4 boxes. All right, so with no CS students, there are this many ways, and those are all illegal because it says I want at least one majoring in computer science. Okay, so try this other way as well. This other way is slightly longer, but in general, by cases, will work all the time. Okay, the subtraction may not work all the time just because there is a principle that I left out of this counting series, which is called the principle of inclusion-exclusion. I might talk about that in a later series, but the reason for subtraction not working all the time is something like that. Okay, third question. What is the value of the variable k after executing the following code? Right, so here we can imagine what is k going through. So k is being executed in here. We're going through 3 for loops, and each for loop has a cycle that goes from 1 up to some number. Okay, so if we only take a look at the first for loop, right, the first for loop is going to go around 10 times, right? So the I1 value is going to go around 10 times, right? 1 up to 10. Now, for every one of these I1 values, I will have 50 I2 values, right? So remember what we said about the product rule, right? So for I2, there's going to be 50 I2s, and then for I3, there are going to be 25 I3s. So for every one of the I1s, there will be 50 I2s. For every one of the I2s, there will be 25 I3s. So if you take all of this down, we just have basically a product rule because we have to satisfy I1 and I2 and I3, right? So the answer here is simply 10 times 50 times 25. Okay, and this is kind of a general idea. Whenever you have for loops that are independent of each other, we just multiply the number of times that they go around. Okay, so this is how many times a variable k gets executed or gets incremented. Okay, so essentially, it gets incremented 1 time, so this would be the answer for k. Okay, question 4. How many binary strings of length 8 have exactly 3 ones? Okay, so there's a couple of ways to look at this problem. Probably the easiest way to look at it is whenever you create a binary string, I always have 8 characters, right? So here are 8 characters, and we have character 1, character 2, character 3, and so on, right, up to character number 8. And these are either 0s or 1s. So all I'm going to do is choose 3 of them to be 1s. Okay, so I'm going to choose 3 of them to be 1s. So choosing 3 of them to be 1s, it's 8 choose 3. So why is it choose? Well, because let's say I choose this one, and this one as a 1. It doesn't matter in which order I choose them, right? So I'm just choosing 3 of them, right? So the second position, the 4th position, and the 6th position here, I'm choosing for the 1s. It doesn't matter if I choose the 6th one first or the 4th one first, and so on. Okay, now the second part of this question is that we have to fill in the 0s as well, but there's only one way to fill in the rest of the 0s. So I guess you can look at this as, how much do we have for 5? Choose 5, right? So we only have 5 left, 5 positions left to choose 5 0s. So this is basically 1, so our answer is really just 8 choose 3. Okay, so how many binary strings of length 8 have exactly 3 ones? So 8 choose 3. Okay, one final one. How many times is the print statement executed? So this print statement in here, how many times does this get executed? Now, this one's a little bit more weird because you'll notice that each of the for loops are not independent of each other, right? So the i's actually depend on each other. So if we think about it a little bit, this question can actually be transformed to say that we are basically distributing these 20 objects, but these 20 objects can be filled into any one of these 3 boxes. So basically what I'm saying is that I1, the value of I1, I2, and I3 will eventually all be these values from 1 to 20. Okay, so notice that I2 ranges from 1 up to I1. So whatever I1 is at the moment, it ranges from 1 up to I1. I3 ranges from 1 up to I2, right? So each of these values, I1, I2, and I3, will take on eventually some value between 1 and 20. Okay, so it takes a second to understand that part. But once you understand that part, we can just say that, okay, now we have 20 objects, and we're putting it into 3 boxes. But this time, it's with repetition. So firstly, I want us to notice that this is not order, right? So this does not have order, right? It does have repetition because I can reuse these objects from 1 to 20, right, in every one of these boxes. Okay, so if we just follow the equation, well, actually, let's look at it another way. So if we want to look at it as kind of distributing candies to people, right? So we can look at these variables as x1, x2, x3, all the way up to x20, right? So all of these variables says how many of them are being chosen. Like how many times are we choosing the number 2? How many times are we choosing the number 3? And they have to sum up to 3 because after all, we only have 3 variables, right? So these 3 variables have to make up some combination of the objects from 1 to 20. Okay, so I'll say that again. These 3 variables have to make up some combination of 1 up to 20, right? And they can be as many times as 3, right? So I could have all 3 variables be 3 if I want, right? Or I can have 2 of the variables be 2, and then 1 of the variables be 20, right? So, so those are all the different cases that I1, I2, and I3 will pop up, right? So, so again, both of these are really the same question where the i's, xi's are greater than or equal to 0. Okay, so we can just plug it into that equation. We can now say the equation is n plus r minus 1. N plus r minus 1, choose r. And so the equation is 20 plus 3 minus 1, choose 3. Right, so I hope this series has been helpful. So as I said, there are some aspects of counting that I've left out of this series that maybe later on I will come back and I will add to. But for now, hopefully this is helpful, and I'll see you guys in the next series.